All right, folks, we are in our fourth class, but this is chapter 12, RAD 1126, New York City College of Technology, copyright, I don't know, 1, 2, 3. It's here for the world to look at. Don't tell anyone. Okay, so I could spend the whole time just on this picture here. It's a really nice picture. Starts off with patient's chest x-ray or somewhere around there, and you have the attenuated image, which means the image is based on some of the radiation that got through, which is usually about 1%, the rest being pretty much heat, and the rest getting stuck in you photoelectrically. The Compton stuff comes out, though. Remember, Compton is when we get an outer electron, and the photon comes in with a certain amount of energy, changes direction, makes it out of the patient, has a little bit less energy than before, but remember, enough significant energy to make it out of you to begin with, hits the image receptor and causes some noise in the form of scatter, or doesn't hit the image receptor and hits you, if you're nearby, or hits mom or dad or whoever might be holding a kid. So Compton scattering and Compton interactions are the source of what we call occupational dose. So when we lower scatter, it's not only better for the image, because if we have less noise, because we create a situation with less scatter, then our contrast goes up, but less scatter would also be good for anyone receiving that scatter. So here's our image with scatter, not as good. And we can only reduce scatter. We can't eliminate scatter, unfortunately. So we remove some of that scatter, and you can see it's still not as good as the attenuated image. You never really see this image, though. But this one here, this scatter removed, is better than the one with scatter. Then we record the image, and we have a couple of classes just based on processing next semester and how all that digital stuff happens. That's when things get a little bit crazy. And then you display an image. I don't really know what they mean by perceived. But you have all these steps. And here is the grid, and here is the image receptor, of course. So you don't get an image unless there's an image receptor, which we said can be film, which we're not using. More likely CR cassettes or flat panel detectors, which then show up on screens. Soon enough, you'll have radiologists like on the bus, looking at their iPhones. They're up to iPhone 11. You should be able to read radiographs at this point on them. Those might be the only people that can afford the iPhone 11. I know I can't. It's CUNY, not Columbia. But okay, I still get the summer off, so really complaining too much. Okay. So all interactions within the patient, so we're talking photoelectric, we're talking Compton, we're talking coherent, but remember coherent's that tiny little piece, will cause some type of absorption. Definitely causing some ionization, right? Because we're knocking out electrons, right? Either photoelectrons for photoelectric or recoil electrons in the case of Compton. And we're going to talk mostly today about where subject contrast is coming from. And we're going to talk about the fact and why, and get a little bit more into it in terms of why one tissue will absorb more or less radiation than, let's say, the adjacent tissue right next to it. So that's the gist of today. And some of it might be a review, because I've already mentioned things like tissue density, thickness, and atomic number, which are the big three. I'll mention them again in 2 seconds if you didn't just write that down. But I'm on tape. Or, I don't know what it is. It's not tape. It's just ones and zeros now. So scatter is going to show up in like noise. It's going to give you a little bit of a grainy appearance. So anything that we can do to reduce scatter, like use a grid, which we'll talk about in another class, but I'm not going to go into it, but grids help reduce scatter. And collimation helps reduce scatter also. So good to collimate. Collimation also is good because it reduces patient dose. If you're irradiating less tissue, then you're getting less dose. But the problem with scatter is, Compton scatter, is that it creates a sort of fog on the image. And it reduces the contrast and makes it a little bit longer scale, right? So it kind of gets grayed out, more grays. More grays than you want. This image, to talk a little bit about absorption, do you guys notice it looks pretty bright in the middle over here? Why? Patella. So you have bone on top of other bone over there. So you're going to absorb a lot of radiation, more than right on top of it, let's say, where you have bone marrow, and that's kind of like, not as dense as the bone on the edges, which is why the edges are bright and the middle is not. But over here, you're having, twice as much, not twice as much thickness of bone, but you have more bone there. And thus, the image receptor in that area, those pixels, however many thousands are in that spot, will be told by the computer to give a lighter grayscale to the actual pixel value. Just how many grayscales can a pixel demonstrate? Well, you can have them turned off so they can be black completely, right? That would be these pixels over here on the sides that represent things outside the field of view, like just outside of the collimation. Anyone? 100 grays? 200 different grays? 256? That's a common number. They double. Usually it's 256, 512, 1024, 2096, and 40 something. The number, I didn't tell this to the last group, so maybe you'll get this right on the midterm and they won't. They have the recording. This is the one that goes up, though. Have you always noticed it's yours and not? Did they ever tell you? It's always the second group. I always get it better the second class around. So the bit depth, D-E-P-T-H, bit depth, that's the number of potential grays that any pixel can demonstrate. So it's always an exponent. It's always x to the bit depth. And it's always 2 to whatever the bit depth is. So it's always 2 to the power of something. So 2 to the power of 8, the 8 is the bit depth. 2 times 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 2 is 256, for example. So a bit depth of 8 would indicate 256 potential shades of gray. Way more than that book. It's only 50.
So is that the base is always 2 and then the...
He got it.
I said that earlier.
Oh, I didn't. Oh, so maybe I did subconsciously. So the bit depth, if I said the bit depth is 9, how many grayscales do you get? It's 2 to the 9th power, whatever that is. We have calculators. It's usually the little caret sign. See, Google is cool because I think you could do this. Where's the little thing here? Do I have it on here?
Just do a little arrow.
Where?
The numbers are just in that little arrow that...
Oh, I see it. I got it. Thank you. You guys are good. 512. Right. Notice we only went up from 8 to 9, but it doubled from 256 to 512. Okay, where were we? So when it comes to contrast, your book likes numbers. Other books don't use as many mathematical examples as your textbook, but it's kind of interesting. So in this first image, compared to the one, I'm sorry, I think I skipped something. Oh no, it's here. Is it? Oh, this one should just be. This one shouldn't have that.
That one's with pathology. The second one's with pathology. The first one's normal.
Yeah, that's why I'm taking this one off. Whoops, did I mess it up?
Right.
This one has no. Oh, that's what it was. Oh, I didn't realize it. I'll put it back then. All right. So this one has no pathology. But what it does have is it has bone and soft tissue, all in the same radiograph. And what this is trying to show you is that you have a combination of photoelectric effect and Compton happening in both of these. But you're getting much more attenuation because of the bone. That's why this is 70 versus 50, right? And you also get a little bit more Compton. And that's because bone has a higher average atomic number, right? Not because it's any thicker, because thickness is not an issue here. They're both the same. So here you add the two together. So between photoelectric and Compton, we have an attenuation factor of 60. It's just 50 plus 10. Here it's 90. It's much higher, which means penetration is going to be less. It's the difference between the two. That's why they add up to 100. And our actual contrast would be the contrast factor, as they call it, would be 90 divided by 60 gives us 1.5. That in and of itself doesn't really mean anything. I don't know what the standard units are. It's just 1.5. The only good it is when you compare it to another image or another example, which is the next one, right? This one has some pathology in it, which causes the attenuation to go up here, right? Because the average atomic number goes up because of the pathology. Potentially some of the tissue density goes up, perhaps. I don't know what type of pathology it is, and we'll talk about tissue density anyway in a minute. Again, it's still not thickness because that hasn't changed. But now when we do the whole math again, and we divide 90 divided by 80, we see that we have gone down in our contrast, right? We've gone from 1.5 to 1.13, which means we have lower contrast. Where am I going with this? This image, if we were to produce it compared to the previous one, should have a longer grayscale because its contrast is going down. So when contrast gets lower, the scale of contrast gets longer, more gray. Just remember L goes with L. Lower contrast, longer scale. Remember, longer scale means more grays and less differences between any one pair of grays. So what is it that makes one tissue different from another? Well, one you have is thickness. And we demonstrated that in the lab with the use of our step wedge for some of you. There was no changes in the step wedge's physical density. It was all one chunk of metal, whatever it was. So the average atomic number wasn't different from one step to another. What was different was the thickness, right? You went up and it got thicker as you climbed up the steps. So I'm going to go over each one of these, but I think thickness is pretty much self-explanatory, right? If I have a thicker part, I need more radiation as well. We did talk about this a little bit. Approximately every 4 centimeters of stuff, tissue thickness. So this is kind of like a rule of thumb, right? Because there's a difference between 4 cm of bone versus 4 cm of fat. However, for test purposes, on average, and for the ultimate test, there's this 4 centimeter rule that says if the thickness is increased by 4 centimeters, you should be doubling your intensity. In other words, doubling your technique, right? Using more radiation. Either you would go up in MA or time, which would double the mass, if you double the MA or double the time. Or you could go up 15% in kV, which should also double the intensity. You can't do both because both would be quadruple. Right? You can't go up 15 kV and double the MA. I mean, you could, but then you would have way over exposure. And you really shouldn't do half-half. Right? You really shouldn't do like, I don't know, I'm going to go up 7% kV and only 50% on the dose, on the MA. Only go up by 25%. Right? It usually should be one or the other. So changes in part thickness. I think one of the most obvious is a chest X-ray, right? You know, you have one exposure technique for an AP, or if I was this way, it's PA, right? But when I turn sideways, you know, the atomic numbers and the tissue density change? No, the same stuff is in there, but the thickness has definitely changed, right? Tissue density is probably the least important of all of them. Because the reality, as it says, I think here somewhere, but before we get to that, I guess I should give you the definition. The tissue density is just sheer numbers of molecules. Right? How many atoms and molecules are there in one tissue compared to another? And the differences are not that big, except in the chest, right? That's the only one that kind of has a significant difference that might actually affect the contrast. So the bone has a very high tissue density. And it also happens to have a high atomic number. So those two are why all the ribs are much brighter. But lung tissue filled with mostly air, I mean, there are molecules in the air. There's no air molecule, but there's different molecules made of different atoms that are in the air. You got nitrogen, you got oxygen, you got some hydrogen. Anyway, the tissue density is much more spaced out in the lungs. So more of the radiation penetrates and gets through the lungs. And when they hit the image receptor feels it in those areas more than others and tells those thousands of pixels in just that one spot, because there's lots and lots of pixels, to be darker on the scale of things. Not necessarily black, but darker. As a matter of fact, the difference can be about 1,000 times more radiation getting absorbed by the bones of the ribs than you have in the lungs. But you don't see big tissue differences in tissue density in a KUB, for example. Right? So the grayscale in a KUB is not that dramatic. The difference between the organs is so close in grayscale that, have you guys seen a KUB? You can't really identify much on a KUB. You see the spine in the middle? Okay, let me see if I can get a picture. I don't know. KUB X-ray? Let's try that. Oh, here we go. Here's some images. I mean, can you see anything? We got spine and we got ribs. Neither of those are part of the abdomen, technically. We got air in the colon, that you can see. Usually you can see the psoas muscles, which are this sort of triangle over here. Do you guys see the lucency a little bit? But, you know, this might be kidney. It's tough, right? You can't really identify that many things. This one looks like it has some stuff on it. I don't know. Maybe we'll take a look at this. Well, see, the only reason, and maybe we'll come back to this later, that you're able to see stuff here is because they use contrast media, which is by far, you know, the best name for what it is. So they're mostly pointing at bone stuff anyway on this, right? Yeah, these are all bony landmarks, not even really anything good. It's too small. I got to log in to see it? No. Okay. Yeah, I mean, they're not pointing to gas. That's the same thing I said. So nothing new in here. That's why CAT scans are much better. This one does a better job, but not really. Bladder, colon. How about liver, spleen, what particular lobe of the liver, appendix? Can't see any of that stuff, right? That's why you need other types of x-rays that have better and superior contrast. So when they say high contrast modality, they're not talking about x-ray, they're talking about CT and MRI, especially for soft tissue. However, we got to start with x-ray stuff. And thanks for joining us, Anonymous Armadillo. So we can break down the major categories of what we do really into 3 or 4 things. You have soft tissue, which might be liver tissue, the spleen, various muscles, kind of lump into soft tissue. Then you have air, and then fat. There's a lot of fat in the body, right? I mean, all your skin and what's under it for a little bit is all fat for the most part. It's different layers. We won't get into that, right? But fat kind of shows up darker. You see this dark area here? Shows up darker than the muscles underneath it because it allows the radiation to penetrate more through it, right? And bones, like we were saying earlier, have a higher attenuation. So that's why it's lighter, because it absorbs more radiation. So the image receptor in those areas don't feel that much radiation. So when I say the radiation that goes through the patient, which we said is not a lot, about 1%, that 1% is kind of spread out throughout the whole image, though. So you are getting more in some areas and less in others. That will allow some interaction between what the image receptor receives in terms of radiation and areas that it doesn't receive anything. Anyone want to take a gather why this area of the bone seems to be brighter than this area of the bone? Well, that's based on thickness, right? So that area of the bone, and I think, is either on top of the clavicle. Well, this is the clavicle, but it looks like it's superimposing some stuff. So it's kind of like the knee where you had, multiple bone on top of each other. Remember, in a radiograph, it's a 2-dimensional image. So everything that you have in your body from here to here is getting squished together and then shown on a 2-dimensional screen, or what used to be just a thin little piece of plastic, right? So when you can get rid of some of the superimposition, then you can also improve contrast. And that's what CT is good for in MRI, because you do slices of anatomy, right? And that allows you to kind of take the lettuce out of the sandwich and look at it instead of trying to figure out where the lettuce is when you superimpose 2 slices of bread and your meat and cheese and everything else. Not kosher. So why is the air black? Yeah, it's outside of the radiation field. So it's like raw radiation. So that's why the air is black here, but not as black here, because even though it's lung tissue, there is still tissue there, right? It's not just, a thin bag of air. So the tissue's atomic number, and when I say atomic number, what I'm talking about is there in a periodic table, there is no tissue element, right? It's the combination of the atomic numbers of the different atoms that make up molecules. Remember, molecules are a combination of at least 2 atoms, at least 2, and then different combinations of those. And if you look at barium and iodine on here, right, those are 2 common types of contrast media that we use. We're using them basically because they have a very high atomic number relative to other stuff, right? So 56, that's a pretty high number for us. So when we increase exponentially, which means a lot, right? When we increase the number of electrons, we will increase the number of both photoelectric and Compton interactions. More electrons to hit, more photoelectric effect, more Compton. In our world, unfortunately, it's very hard to see hollow things. So it's hard to see the stomach, it's hard to see the colon, and for all intents and purposes, it's hard to see blood vessels, even though they're not really hollow. I mean, they have blood flowing through them. Not like just straws, there's nothing in them. But needless to say, when we're doing an angiogram, so that's an investigation of the vessels, whether it's a femoral angiogram or I had a cerebral angiogram once upon a time. We wouldn't put barium into the vessels, that will kill you. But ionated contrast, we inject all the time. In fact, you guys will have to inject, especially if you want to do CAT scan. Don't worry, they train you for like an hour. Like, stick these 3 people. Oh, you got 2 out of 3 right? All right, you're good. Send that off to Albany. You think I joke. Some places give you more training than others. Okay. Now, if you look at carbon here, not as many interactions, right? So, you know, if you want to visualize a tissue that has carbon in it, you got to hope it has some other things in it too. I just had this thought that I would swallow a piece of charcoal and then have someone x-ray me to see how well it showed up. Nah, maybe not. In theory, it should not show up very well, right? You might see the outline of it.
Why wouldn't you just x-ray the truth instead of swallowing it?
That is actually doable. That's why. I don't want to give you examples of things we can actually do. No, yeah, let's try that. But you got to get the real charcoal. Like, you got to get like the real Asado Argentine charcoal that's made out of like real wood. Right, not like wood bricks. You have some?
No, what's that charcoal, that active charcoal that you can drink?
Oh, I don't want to pay for that. No, but yeah, I don't know. Is it 100?
What's the difference?
But the question is it really made out of carbon or is there other stuff in it? Right, there's probably a bunch of stuff in it. You know, it's not pure carbon. I don't think. We'll Google it later. All right. Or no one says Bing it, do they? Let's Bing that. Let's ask Jeeves. No, that just goes over everyone. Okay. So contrast media is going to be good in something like the stomach. And up here, you're kind of getting what's known as a negative contrast because of the air. The air actually is showing up blacker against brighter stuff, which is the only reason you can see it. And barium has an atomic number of 56, which is pretty high. I told this to the other class, and you know they'd be upset if it wasn't on the recording. So when I had some connections when I was a student, and I needed a barium GI, and I was able to get my barium nicely mixed and cooled down in a refrigerator, and best of all, it was strawberry flavored. So all that is gone now. Now you get lukewarm, white, pasty, because someone had to get all upset with the red number, whatever they put. It only takes one person to get allergic to something, and there goes your strawberry flavor. It wasn't great, but it's better than what you have now.
They like calling banana.
They used to. I don't think any of that exists anymore. Now they just have thick and thicker, which is not great.
But it's like orange. They have the map or?
At the hospital? Oh, they must be FDA approved then.
Yeah, they definitely have like bananas, so.
You know, the Food and Drug Administration, this is an aside, governs X-ray equipment, not just food stuff. X-ray equipment comes under the FDA. Check it out, it's true. So this poor person, what I love about this is it looks horrible, and this is after the surgery. And it's still all convoluted, still all busted. So this is a knee, if you didn't know. So you can see the patella in profile. This is not a very good knee because the condyles are not superimposed. But we're here to talk about this big thing in the middle that shows up and jumps out at you. And that is, maybe it's made out of titanium, at least the book says it is. But I don't know. It's definitely something steel. And because of its atomic number, it absorbs a lot of radiation and shows up much brighter against a darker background. So tiny little things like staples, and I didn't mention this in the last class, but this is really important. This is why you have to get people naked a lot, right? Because zippers, buttons, anything metal, earrings, okay, certain piercings you just can't take out, and they're used to that by now. But they show up, and anything that is superimposed on top or below of a piercing or whatever metal object is in there, you can't see it. It's gone for all intents and purposes, right? So putting on gowns, and as much as they're kind of terrible, the paper gowns are probably better radiographically speaking than gowns that have little metal snaps that close. Because those show up all over the place. They just didn't have us in mind. Plastic snaps are a little bit better, but they still show up. And as our imaging gets better, it's hard not to see this stuff. So where's my, aren't I recording this? Did I stop? Oh, I'm here. So scatter. Scatter shows up like noise. Remember, noise is a great appearance. The problem with noise is a lot of bad things show up as noise. If you don't use enough radiation, that shows up as noise. If you have scatter, that shows up as noise. It's kind of hard to sometimes figure out where the noise is coming from. I mean, you have mechanical noise, just from the machinery. If you really want to go crazy, you have quantum noise, right? We actually use that a lot. We call it quantum model when you don't have enough radiation, not enough quanta. Everyone has quanta is it's like a gaggle of geese. So a quanta is like a bunch of photons. Sometimes I picture them. I don't know, what does a photon look like to you? Squiggly thing with a wavelength? Like a bunch of snakes that you can't see coming out of the tube? But if you don't have enough of them, they create noise. Now this is an extreme example, right? It looks a little creepy, like Halloween costume. Coming up soon, Halloween. Go out, get your fake blood. Get everything on Amazon now. My daughter wants to get knives that are fake, that they retract, so you can stab someone with them and it looks like they've been stabbed, but it actually goes back into it. I'm like, you're gonna get detention for that if you bring that to school. Or worse, arrested. Which is more like it nowadays. Everything is too extreme now. You can't do anything anymore. No more fun. But noise, we can try to reduce the noise that you get from scatter by utilizing things we mentioned before, maybe grid, which we'll discuss in another class, or using less kV. But I'll show you using less kV will not give you much less noise, which means we can actually use higher kV, generally speaking, because kV, when I taught this class don't know, 5-6 years ago, before we kind of went completely digital and before the content specs changed, where I had to talk a lot about film, KV was known as the controlling factor for contrast. So yes, you can still say KV up, contrast down. But KV is no longer the controlling factor for the contrast of the image. Now, when we window the image digitally, we can control the contrast. And KV, as long as we penetrate the part, we can actually use a little bit higher KV than we used to use, which is better for the patient. Now, you can't blast it completely. You can't use 120 kV on a finger, because then you'll have too much penetration, and then everything will be black. The image receptor will feel too much radiation, and then you won't have a good image. But you could use a little bit more kV. And you will get more scatter. You will get more Compton. Just think about it. Remember, Compton, X-ray goes in with a certain energy and comes out with a little bit less. But if you have higher energy to begin with, more kV to start with, you have more chance of having Compton than you have photoelectric. And the opposite is true, and you'll see this on the next couple of slides. You'll see at a certain point, photoelectric just stops when the kV gets too high. So maybe we should talk about that right here. So photoelectric, you're getting at low kV, like 20 and 40. Now remember, you might have started with a higher amount of kV, but by the time it goes through the process, it's going to be in these lower levels. Remember, with a single phase generator, you're getting about a third of what you set anyway. So these are quite possible, right? And Bremsstrahlung, right? The further away you get, the lower the photon energy comes out, no matter what you started with. But so at low KVs, we're getting a lot of photoelectric. But then at around, according to this one, 58, 59, somewhere just before 60, what happens after that? Gone is photoelectric. Whereas Compton, I don't really agree with this one, actually. Compton looks like you're getting a continuous amount of Compton. But if you ask me, and I joked that I should contact Carol, the author of your textbook, if you ask me, this should be more like, if this were a seesaw, I should push down on the Compton so that this goes up a little bit. Because when you go up in KV, right, you should get a higher relative number of interactions. So this really should be, downhill. This should really be uphill, I think. But regardless, you're getting Compton interactions at every KV level. And after a certain point, it's pretty much all Compton, which sounds really bad, right? Because, more KV gives you more scatter, right? Scatter goes up with increased KV. Do you really see it? I'll come back to this in a second. Here's an example, right? I really should maybe switch that around. So here are two radiographs. Does one look better than the other? Well, they definitely look different, but not so bad. It's too bright in here, right? Getting maybe we can pull down one of the shades. Because I realize the lights are off already. What they did here, yeah, that's better. That's good. That's good. All right. So what's happening here? So first of all, these were done with film. But it says that there was a 15% increase in KV, which should give you more scatter, right? And radiograph A was done at 80 kV at 40 mass. Radiograph B on the right side was done with 92 kV, which is exactly 15% more than 80. And half the mass, so 15% rule was involved in here. But the fact that it went up from 80 to 92, do we see much scatter? Does it look, well, these are not digital, so we can't even really use the word noise. When it comes to film, we would say fog instead of noise. But let's just put it this way. Does it look worse? No, not really. So, even though there's more scatter, Not even with film, it's not much of an issue. And it's even less of an issue now because the algorithms that we use really correct for scatter and contrast in general. So we should use higher KV. And the techs out there, especially the older techs, myself included, but now I've learned, well, I've been teaching the class. But we used to, for a hand, we used to use 52 all the time. 52 at whatever mass. Now we can use 62, 65, and lower the mass considerably, right? And lower the dose. I mean, you don't lower the dose completely because remember, when you do increase KV, you do get an increase in intensity as well. Remember, we had that image where you had the circles, and right? But you can lower the dose significantly by increasing the KV. Remember, you can't go up like 90%, right? Because then everything again will be black. So in terms of contrast agents, again, I think this should be an upward kind of Compton. But you can see that when you add iodine, which is twice as much atomic number than the combined atomic numbers from bone, you get even more photoelectric effect. And what iodine actually does when it gets into the system is it will actually bind to the other molecules nearby, increasing their binding energy. So when you increase the binding energy, it makes it even harder for a photon to knock out an electron, which means photoelectric effect is going to increase, right? Because you're left with even less energy, because all of the energy, a lot of the energy anyway, goes to trying to knock out the photon, which will be successful, but your photoelectric effect goes up because there's not much energy left over after that binding energy has increased, and thus photoelectric effect goes up. Right. So contrast media, which I said is the best name for this thing, because contrast media is designed to increase contrast. It's one of the few things that's named the way it should be named. Contrast media increases contrast. But it also technically increases the dose to the patient. Right? Photoelectric effect is the dose to the patient. So if you want those angiograms, then that's what you're going to get. So let me show you an angiogram, just so you get an idea of, I think I had one up here before. Where was I? Maybe I'll just do it again. Let's see. CT angiogram. Right, so the vessels look white, right? And that's because the ionated or non-ionic type of contrast media fills up the vessels, right? Increases the photoelectric effect happening in those areas, so they show up nice and bright. I mean, there's a lot of other stuff going on with these images, but some of these are pretty cool. This one. Where am I? That's pretty cool. They made them blue, too. That's a runoff. Who said that? That's good. So what you're seeing here is contrast in the vessels, but what you're also seeing is what you're not seeing is the rest of the soft tissue. So the soft tissue is removed because the computer is very good at assessing the pixel values. So before it even shows up, it knows that the soft tissue surrounding the vessels would be lighter. And basically, there's an algorithm that says, take out those pixels and turn them black so that they don't show up. And then you're left with nice vessels. which is pretty cool. And then you could do even more fun stuff. Like you can reverse the image. I had one of these done. Right. I had a cerebral angiogram. I've had all sorts of stuff done, by the way. But here, what they did is they took those white vessels and they made them, let's see if I can make that bigger, and they made them black. I lost a little bit of resolution by magnifying it, just like X-ray. But they took the white ones, and this is darker because at one time it was brighter because it's a much larger vessel. Is that the basilar artery? Anyone know?
That's definitely what it is.
Yeah, when you take the CAT scan batches, you learn everything. So, but here they did the same thing. They MIP'd it out, maximum intensity projection, and they were able to get rid of the soft tissue based on its individual pixel values and getting rid of them and only demonstrating what you want. And then they've done fun stuff like, I don't know, let's see if we can get one. I saw one earlier. Let's look up cow. Cow and chicken? Let's see if we can get a video. That's not it.
You can spin it now.
Okay, welcome back. This is video part 3.
That's not me. But here's the circle of Willis, cow, C-O-W. And I don't have it here, but yes, they can rotate it, right, and do all sorts of fun things once you have it done. All right, we digress, and we're almost done. So what we're having here is we said that the contrast agents will increase the binding energy, and then in addition to that, having a very high atomic number themselves are going to give us a lot more photoelectric interactions. Right. So then we can see the vessels. So we are finished, but what I can do is I'll turn this off, and since I did it for the LEC, a little bit about the, am I on here? Where am I? Pause recording. No, I want to